predictable system, such as when a ball drops onto a flat surface, the behavior of one ball closely matches the behavior of others dropped from the same height. There will be small discrepancies, but plotting the path of the first ball allows you to approximately predict the paths future balls will take, and be right. Bouncing a ball off some round white pegs changes everything. Now, knowing the path of one ball will not help you to predict what the paths of others would be. This is the butterfly effect again. Tiny variations in the paths of the balls are being amplified on every bounce, making prediction impossible. This match is igniting a video version of the butterfly effect known as feedback. This picture is being generated by a camera which is pointing at its own output on a nearby TV screen.
If we just shut off that picture, you see that as the camera looks at the monitor and doesn't see a picture, it won't reproduce one. So to start a picture, we should somehow ignite it. And as we do that here, we just put a little bit of light in the center of the picture, which is seen by the camera and then fed back into the monitor, and the process gets going. The process of video feedback. But I guess you would like to know, do we understand the pattern? Can we describe how the pattern is emerging? And I think the honest answer to that question is no. But to convince you how difficult the question is, let's change the setup slightly. And one way to do this would be, for example, to just rotate the camera slightly around its axis. And maybe we do this at this point. And as we do that, you see, by just rotating the camera about a degree or two, the picture resulting in the feedback system is totally different.
The video camera is scanning the monitor 50 times every second. But because the camera system is never perfect, tiny distortions to the picture are created by the camera's electronics, the lenses, and the monitor itself. Camera distortions, represented here by the letter C, are added to the original picture to create a new but significantly different picture on the monitor. The camera sees this new picture and alters it again. Each frame changes from the preceding one as the system repeats the process over and over. If C changes, such as by tilting the camera, then the type of image changes. This process of repetition, or iteration as it's known, is something that computers are very good at doing. But computers need numbers, not pictures. So, change the pictures to a symbol, X, and the mathematical equivalent of feedback might look something like this. The interesting part is what happens to X when you change C, the equivalent of tilting the camera. Sometimes the variations in X will smooth themselves out, and at other values of C, X may seesaw periodically from one point to another. But at certain other values of C, the resulting X's will bounce chaotically in a patternless sequence. One of the surprises of chaos is that all these different behaviors can be displayed in just one system. This computer simulation shows the behavior of a particular kind of pendulum, a double pendulum. Sometimes it will follow a regular path, which it will repeat forever. It's a prisoner on that path, tracing out what is known to mathematicians as its attractor. But nudged slightly harder, a subtle change occurs in the motion. It still looks periodic and regular, but it's not. It never actually repeats itself. It has started to follow what has come to be known, somewhat mystically, as a strange attractor. Strange attractors are the hidden patterns of order in disorder, the structure within the chaos. This is the strange attractor that lies behind Edward Lorenz's early weather models. It's a computer representation of the rules which generated his apparently random results.
When I first drew up the attractor, this was before the term attractor had been introduced, and I think in meteorology you could identify attractor with climate. It's a set of states which do occur as opposed to those things that don't happen.
Mapped out in an imaginary mathematical space deep inside the computer, those weather states that do occur trace out this beautiful and appropriately butterfly-like shape. Each point on the light blue lines represents a single condition of the world's weather, and as we follow the little red cursor, we are seeing the weather unfold in time in the computer's mind. There are an infinite number of possible pathways which the weather can follow on this, the Lorentz attractor, and yet paradoxically those pathways never cross, even as we swing from one lobe of the structure to the other. Where then is the chaos in such an apparently well-organized pattern? The chaos derives from the attractor's ability to behave like a mathematical food mixer, jumbling up the constituent elements of even a simple straight line until each point on that line is traveling in different directions. The line is stretched and folded repeatedly, like so much dough. This is, again, the butterfly effect at work. But Ed Lorentz also indicated that there are states of the weather system that do not occur, that are not allowed, and that the points representing those improbable states, shown here in red as the edges of the cube, are like snow in the Sahara or heat waves at the South Pole. Puts the attractor, sucked in until the system is once again its old, unpredictable self. In the new science of chaos, it seems the closer you look, the more you see. Even a dripping tap, regular as clockwork, indeed the basis of many early timekeeping instruments, turns out to have a chaotic trick or two up its piping. It is one of many dynamic systems showing a type of behavior that has convinced many scientists that the rules of chaos are universal. When you gently increase the water flow, the drips start coming in groups, then longer groups, then even longer groups, until the cascade is truly chaotic. Amazingly, even here it seems, there's a mathematical rule at work. A rule that describes one of the pathways from order to chaos. A rule that has come to be known as period doubling.
In the period doubling route, you start off with the system being in a periodic state, a simple periodic state. And as you change the parameter, this periodic solution changes its period, it doubles in length. Then it quadruples as you increase the parameter further, then it eight-tuples, and so on. This sequence occurs very, very fast, and very, very quickly the system becomes chaotic. Let me demonstrate it by this electrical circuit, which is based on a simple radio valve. Well, the circuit's off at the moment, so the state of the system is attracted towards the most simple possible sort of attractor you can have, a simple point attractor here. When I turn it on, the circuit will start to oscillate, and you'll see this state get attracted towards a periodic attractor. Here's the periodic attractor. You saw how quickly the state got attracted towards it. Now I'm going to change one of the settings in the circuit, and we'll see the attractor evolve and go through a sequence of period doublings. There, it's period doubled. Let's change it a little bit more. There's a period 4. You see that now there are 1, 2, 3, 4 revolutions that go around. Now I'll change the parameter very, very slightly. And already we've got a strange attractor.
In 1975, a young physicist was working on the problem of how frequently this doubling occurred in two totally different and unrelated systems. Although the now familiar dark regions of order in the unfolding chaotic cascade were no longer much of a surprise, when he compared the rate at which each different system was doubling, it was clear that something very odd was going on.
I immediately realized there was the same convergence rate, and in fact, those numbers were the same, which was a completely extraordinary result, because what it meant was that there were two completely different problems that I had considered, and yet a number came out that in no way depended on either of the problems. And then, of course, you have to start wondering to yourself, what then does it depend upon? So I set about trying to figure out what it depended upon, which produced the theory of period doubling, and as its hallmark has the property of universality, which is exactly to say that the measurable things in any one of these very different systems is always precisely the same. And this constant, about 4 2/3, is one property that's the same for all of these different systems.
To apply the lessons of chaos to complex systems, mathematicians draw pictures of the behavior. As we watch this circle distort into ever new, curious shapes, it's hard to believe that they're all, even the original circle, computer representations of that